go through one slide maybe. Yes, it's good. Yeah. That usually
Testing. Testing. Okay. Cold, so anytime you leave your homes, it must be for a special occasion. My name is Dr. Quirk, but y'all can call me Amanda. I'm a lecturer here at Columbia, and I'm the outreach coordinator for the astronomy department. Now, a lot of new faces. Raise your hand if this is your first time. Awesome. So exciting. Thank you for spending some of your Friday night with us. We're going to start with some trivia. So we love to see what prior knowledge you're coming in with and then to see how much you learn. I'll talk about the rest of our spring schedule, and then we'll have Dr. Peter Rouse talk, and then we'll do Q&A and a raffle after. And unfortunately, we are not stargazing or observing tonight because of the clouds. If astronomers had a superpower, it would be to get rid of the atmosphere. That would be very bad for us, but astronomers for a split second would be thrilled that they didn't have the clouds in their way. All right, so the way trivia is going to work, there are 4 questions. Question 1. Why is a neutron star called a neutron star? So how this works is I'll give you time to think about it, and collaboration is encouraged. Talk to people around you, share your ideas, and then after some time, I'll say 1, 2, 3, vote, and you'll show me 1 for A, 2 for B, 3 for C, 4 for D, and 5 for E. Make sense? All right, talk amongst yourselves and think about it. All right, I see some people already with confident answers. 3, 2, 1, vote. Let me see. All right, I'm seeing lots of 4s, some 3s, 1, 1, 1, 5, some 2s. Oh, we got all of the answer choices. Let's see what it is. Ooh, kind of a trick. It was 2. Please. All right, we've got some excited folks and some surprised folks. As scientists, we always love to be wrong because it means we have learned something or we have the opportunity to learn something. So in science, it's much more exciting when our guesses are wrong. Question 2. What is the heaviest element that can be produced through nuclear fusion? So once again, think about it, talk to people around you, share your knowledge. This time we promise there is only one answer. All right, let's vote. 3, 2, 1, vote. All right, I see a lot of 2s. I see some 5s, some 3s, some 1s, maybe no 4s. All right, and it is iron. So once a star makes iron in its center, it is in trouble because it can't make anything else, so it will run out of fuel. All right, question 3. Some history. Who first discovered neutron stars? Okay, let's see those answers. 3, 2, 1, vote. All right, we've got a 3 on the projector. We've got some 5s, some 2s. I don't. All right, get ready for our last question. I do have to warn you, we always end with our most serious and most difficult question now that your brains are warmed up. So a neutron star has enough space to fit 1 trillion elephants. How many elephants does it weigh? There's lots of good debate going on. Let's see what you've come up with. 3, 2, 1, vote. All right, I see 4s, 3s, 5s, 2s. Maybe no 1s. All right, and our answer is 450 septillion elephants. Not in my head, I can't do the math. Oh, if you would look up how much an elephant weighs. So this has to do with density. Yeah. All right, so astronomers, we do use funky units. We don't use elephants, but it's always fun to think in a different unit for a mathematical problem. Okay, our best way to find out about our events is to join our mailing list. It's on our website. We send out advertisements about the talks with the registration form. We do have a talk every month this semester. Our next one is March 6th. Then we have April 10th. Both of those will be at 7 p.m. like tonight. Our May 1st one, we have to make it 7:30 because the sun will be out a little bit later, and we want to make sure that we can observe if the weather is good, and fingers crossed we'll have good weather.
All right. Can you hear me, y'all? Can everyone hear me? Okay. All right. Thank you very much for being here for this talk. I hope everyone learned something. So yeah, my name is Peter Rao. I am a postdoctoral researcher in the Columbia Astrophysics Laboratory, and I'm going to tell you what's inside neutron stars and how we know it. So the Big Bang created hydrogen, helium, and lithium, mostly hydrogen. And every other element that's heavier than that was created either directly through nuclear fusion or through other processes which involve the elements which were created through nuclear fusion. And so the lives and deaths of stars are essentially a competition between the gravitational force which is binding the star together and the pressure produced by the nuclear fusion occurring in the cores of these stars. That pressure is in the form of radiation pressure, so the light itself created in the fusion process, is pushing against gravity, and also the heat produced in this process causing the gas on the star move faster and push harder against gravity. But in the end, gravity wins. And less than maybe 10 times the mass of our sun will follow left-hand path here, where you end up generally with like dwarf or the mass, about the mass of the sun, maybe a bit less, and with a size comparable to that of the Earth itself, so much smaller than the sun. But for heavier stars, something a bit more explosive. So cosmic stars with a mass greater than 10 times the mass of the sun. These stars will have heavier elements than trivia. The Earth will be iron, but heavier stars will be fusing and eventually they run out of nuclear fuel. You can't get other elements. So they elements are heavier than iron. Once that limit, star will core of the star runs so much in fact that the star will push back on the matter and eject again. That is supernova. And mass is less than 25 times the mass of the sun will form a neutron star, and it is greater than that black hole. So we're going to be talking about neutron stars. I think the original black hole. I hope why. So this is a size comparison of neutron star to city which we're now sitting. Okay. The rover is there, and neutron star is diameter about the same size as Manhattan. Within the neutron star is mass of maybe between 1 and 2 suns. So these are extraordinarily dense objects, extraordinarily small, and extraordinarily dense. The neutron stars are laboratories for extreme physics and extreme astrophysics. For the massive stars remaining after supernova, they're dead. They're no longer undergoing most like that is left in the star. That's all it has really. Exceptions, but it basically cools off over binary. Many of them will just sit there. And they're pretty compact. So the density is that of the comet. So in densest matter in the universe outside the black hole. So densest matter is compact. Not the singularity black hole that's affected by an event horizon. So this is then occurring. At the surface of the stars, gravity is the outermost layer of the neutron star is almost iron. So this iron is that density really times that of iron. How strong gravity is. You go inward, the density increases until you get to the innermost part of the star, where the density is 5 to 10 times the density of per hour. So that is in metric units, 10 to the power of 15 grams per cubic meter. So 10 multiplied by 12, 15 times grams per cubic meter. We're going to leave half for really small. And that is sort of hard to get a grasp of things. So what? How do you imagine how massive, how dense that is? Okay. Pardon? yes. Is that better? Good? Okay. Okay. And so one way to think about this is, well, how does, let's take a spoon full of the matter from the center of a neutron star. So while this spoon has been exaggerated, a spoonful of that matter, how much would it weigh? About the same as Mount Everest, approximately. So again, it's hard to estimate these things. How heavy is Mount Everest? We can make estimates. Exactly how much of a spoonful you get, exactly how deep you go. But this is, give you a hint at how extraordinarily dense this matter is. They're also the most rapidly rotating stars. So your typical neutron star will be rotating once every second. And the record holder is rotating with a period of 1.4 milliseconds. So it rotates 700 or so times every second. And these most rapidly rotating stars come in binaries. And so these are neutron stars which have matter falling in on them from another star, a star close, maybe like a white dwarf or a star like our sun. And this matter that spirals in on the star will cause it to spin at a faster and faster rate until it's rotating, up to maybe 700 times a second. So imagine an object, the size of a city that weighs as much as the sun or more and spinning 700 times a second. Remarkable. They also have the strongest magnetic fields in the universe that we know of. And so the most common class of neutron star is what's called a radial pulsar. And they have magnetic fields with a strength 10 to the power of 11 to 10 to the power of 13 Gauss, and I'll explain what Gauss is on the slide. Magnetars, which are a rarer class of neutron star, have magnetic fields which are even stronger than that, typically a factor of 100 to 1,000 times as strong as those of radial pulsar. Now, again, if you're unfamiliar with what a Gauss is, don't worry, it's not that commonly used. So a Gauss is, you have 10,000 Gauss in a Tesla, which is the SI unit of magnetic field strength. And so some typical values, so you get your bearings for how much Gauss is. The magnetic field of the Earth is about half a Gauss at its surface. Your typical fridge magnet has a magnetic field of strength about 50 Gauss. And an MRI machine, which is essentially the strongest magnetic fields that humans produce on Earth, with exceptions, is maybe 15,000 Gauss. So the magnetic field possessed by a neutron star is, what is that, a factor of maybe 1 billion times as strong as an MRI machine's magnetic field. And if you know about what these do to any jewelry you're actually wearing them. Imagine wearing some jewelry going near a neutron star. It's a nightmare. So how do we know any of this? All right. These are extraordinarily small, city-sized stars. There are none particularly close to us. The nearest, I believe, is 400 light years away. A lot of good thinking, theoretical physics, and modeling. But it all starts with nuclear physics. So our knowledge of nuclear physics begins in the late 19th, early 20th centuries when we found that the atomic picture was correct and that in the center of every atom is a nucleus. So your atom has electrons orbiting around a nucleus. Of course, it's not this pretty. It's more like a cloud of electrons. But this picture of the nucleus is correct. The nucleus is formed of positively charged protons and neutral neutrons. And the electrons are attracted to this positively charged nucleus. Now, this picture is deceptive because the atom itself is about 100,000 times as large as the nucleus. But almost all of the mass in the atom is within that nucleus. So essentially, all of the mass is within 10 to the power of -15 of the volume. So most of what we see, formed of atoms. Everything we see is formed of atoms, light. And all of the mass in those atoms, almost all of it, is confined within an extraordinarily small fraction of the volume of those atoms. So there is a lot of empty space in everything. So then the question could be asked, okay, what happens if you get rid of the empty space? What happens if you start smacking these nuclei together? And so this led to this proposition by a famous physicist named Lev Landau in a short paper in 1932, when he argued that in the center of some stars, the density of matter could become so great that the atomic nuclei come into close contact and form one gigantic nucleus. He could not call this a neutron star because the neutron had not been discovered yet. It would be discovered shortly after he proposed this, although people were thinking about neutrons before they're actually discovered. But the name neutron star came about a few years later when we had two observers this time, Walter Baade and Fritz Zwicky at Caltech, who proposed that supernova explosions, which had been observed, in fact, had been observed by humans for at least 1,000 years or so. I think that's the first recorded supernova explosion. And that these supernova explosions would leave behind these extremely compact neutron stars. None has been observed at this point, but this led people to start looking for hints of these neutron stars in nature. But the theorists went ahead of the observers in this case, and later that decade, the Tolman-Oppenheimer-Volkov equation was developed. So these theorists realized that a neutron star would be so compact that its structure could not be explained by normal Newtonian gravity theory. You'd have to use Einstein's theory of general relativity, because the matter in a neutron star is so dense, the pressure is so high that the pressure force, or so the pressure which is pushing against the gravity, is actually contributing to the gravitation itself. It's making the star even more compact. So you have to have extremely high pressures to push against the gravity, but those pressures increase the gravity. So you get these extraordinarily compact stars, and they predicted, particularly Oppenheimer and Volkov, that the maximum mass of a neutron star would be around 3/4 of the mass of the sun. So there was a gap between the there were some accreting X-ray sources which turned out to be neutron stars, but people were not sure at the time. The first smoking gun hint, or sort of confirmation of a neutron star, though, was, of course, by this lady, Jocelyn Bell, or Bell Burnell, in 1967. So this is Jocelyn Bell standing in front of the Interplanetary Scintillation Array, which is the radio telescope that was used to detect the first neutron star. So that neutron star was first called a pulsar, which is pulsating star. And it was detected by Bell in 1967, first on August 6th, and then later on November 28th. So, confirming that, what they'd seen is real. She was a graduate student at the time, working with Professor Anthony Hewish. And this object would later be called PSR B1919 plus 21. Astronomers have funny names for things. They jokingly called it LGM1, Little Green Men 1, as if there were aliens producing this radio signal, because it's so, it was nothing like we'd seen before. It's extraordinarily regular pulsed radio emission with a period of 1.34 seconds. So every 1.34 seconds, the telescope was seeing a beam of radio waves, and then it turns off, and then every, feeding itself. Very regular. And they confirmed that it had to be astronomical. It could not be from, some machine somewhere that, they're fortunately detecting. It was from space. And of course, theorists get very excited about this, and it didn't take long for someone to connect this with the idea of a neutron star. So this was Tommy Gould, who wrote a short paper a year later proposing that pulsars are in fact rapidly rotating neutron stars, that they are, again, a neutron star, and it's producing a beam of radio waves from each of its poles. And as this beam sweeps by the Earth, we observe, or can observe, these radio waves. Of course, you could have neutron stars or pulsars which are not pointing at Earth, and then we don't see them at all in this way. I do not believe this radio beam was expected to be produced by the neutron star. So theorists can predict things, but nature likes to surprise us with things like this. So how do we get from this observation of this radio source, this star spinning around in space with a radio beam pointing at us, to the size and composition of these objects? Because most of the neutron stars that we observe we just observe these radio pulses from them, but the vast majority, that's all we get. Well, the fact that the star is rotating so rapidly, as inferred by the fact that it is spinning around, produced with this radio beam sweeping by the Earth every second or so, implies that it has to be very compact. So imagine we're standing on a rotating star. You'll be experiencing two forces on you. You'll have gravity, which is pulling in on you to keep you bound to the star, but also you'll be experiencing a centrifugal force, which is pushing outward on you. The force of gravity on you increases with the mass of the star, but decreases with the radius of the star, how big it is. So to have the gravity on you acting as strong as possible, you want the star to be extraordinarily dense. Meanwhile, the centrifugal force, which is pushing out on you, trying to fling you off the star, increases with how far away you are from the center of the star and with how fast the star is rotating. So this says that if you want to spin around very quickly without flying off the star needs to be extraordinarily compact, particularly if the star is spinning. If the star rotates too quickly, matter will be flung off it because this centrifugal force will win out over gravity. So let's think about what would happen if the sun was rotating faster. How fast would the sun have to be rotating to fling off matter in this way? And the answer is it'd have to have a rotation period of 2 hours and 45 minutes. So it'd have to rotate faster than the Earth rotates. The Earth once every 24 hours. The real rotation period for the sun is 25 days at its equator and maybe 5 extra days at the pole. It actually rotates at a different rate at different parts of the sun. So it's rotating not nearly fast enough to eject matter in this way. Meanwhile, neutron stars, being more compact, maybe let's say a neutron star, which is about 1.4 times the mass of the sun, and this is the typical mass, they would start ejecting matter if their rotation period was 0.6 milliseconds. So they could rotate essentially, what's that? Over 1,000 times a second without ejecting matter, just based on how strong the gravity is on their surface. So essentially, the fact that these objects are so compact allows them to rotate so quickly. So actually, how do we measure this mass, though? Because this is not actually a direct measurement. This is just inferring things. And we actually can measure some of the masses with remarkable precision. So the way we do this is with something called the Shapiro delay, which is the fact that light from a partner star, so if we consider a neutron star and a binary, and maybe I'll go back and watch the video again, rather. Here we go. Light from a partner star, let's say up in this upper left corner, will be bent around the strong gravitational field of the neutron star. And this bending will leave behind a delay in the light that reaches us compared to if the star wasn't there at all. And we can actually use that delay to infer what the mass of the object, in this case, the neutron star, is that's in the way. And this allows us to, again, measure the masses of neutron stars to remarkable precision if they happen to be in one of these binaries systems. And the record holder is 2.16 times the mass of the sun. So they can be, twice the mass of the sun, basically the same size as the lighter one. We can also measure the radius. And the radius is a bit trickier to measure, but we do have some measurements of it. And the best way to do this is through a telescope called NICER, the Neutron Star Interior Composition Explorer, a bit of a contrived acronym, but it works. And so MICER is an X-ray telescope on the International Space Station. And what it does is measure X-rays traveling to us from hotspots on the neutron star. So these hotspots are probably produced by particles hitting the surface, following magnetic fields and crashing into the star and heating it up. About the radius of these objects. And so we have measurements for the radius. But how do these objects support themselves, right? So we've sort of said what the size is, maybe what is providing this pressure to counteract the extreme gravity. And this is something which I've termed here particle degeneracy pressure. For more of those who are more technically inclined, this would be fermion degeneracy pressure. And this says that no two neutrons, protons, or electrons can occupy the same state. So we can think of this as a ladder. So maybe we can fit two of these electrons per step on the ladder, and these are neutrons, and once the ladder, the neutrons are, the more pressure they provide to counteract the gravity of the star. So this neutron degeneracy pressure, or sort of the principle behind it, is the reason that bulk matter occupies volume. It's sort of extraordinarily fundamental importance in chemistry and in the structure of everything we see around us. But we're really pushing it to extremes in neutron. So this type of degeneracy pressure exists in both white dwarfs and neutron stars. And in white dwarfs, it is the degeneracy of the electrons. So the electrons are the ones which are climbing up this ladder here, which is supporting them against collapse. The electron degeneracy pressure, again, allows you to have the mass of the sun within an object the size of the Earth. Neutron stars are so dense that the electron degeneracy pressure is no longer enough. You actually have to start combining electrons and protons to creating neutrons, and it's their degeneracy pressure which is supporting the neutron stars against collapse. A neutron star, of course, much smaller than the white dwarf. It's a city-sized star as opposed to an Earth-sized star. But neutron degeneracy pressure is not the only thing which is contributing to neutron stars' pressure. Understanding matter at the densities of a neutron star requires that we understand things about nuclear physics. And thankfully, we do. In particular, we need to know something about the strong nuclear force, which is the force which binds nuclei together. Now, nuclei formed of neutrons and the protons like to repel each other. They're positively charged. Preferably they would just blow themselves apart. But the neutrons, if you combine the protons with the neutrons, you get what's called the strong nuclear force, and that holds the nuclei together. For them to support higher masses. So if all you had was neutron degeneracy pressure, you'd have a neutron star with a maximum mass of around 3/4 that of the sun, as Oppenheimer and Volkoff predicted. But if you add extra pressure, as you can get from the strong force, then you can have a more massive star. We combine our knowledge of terrestrial nuclear physics experiments, like this one here. This is an experiment at Michigan State called FRIB. And you combine that with theory experiment. So let's actually take a trip inside the neutron star now. So we'll start off we'll go out, in. So first we find the ocean of the star. This is not a very deep ocean, maybe a few centimeters, and it's mostly formed of matter which has fallen in on the star after it's created in the supernova. There's light elements, some iron, and it collapses onto the surface. Once you go deeper than that, we get to the crust of the star. Because neutron stars, unlike most stars, have a solid crust as their exterior. This crust is a crystal lattice of positively charged nuclei surrounded by electrons. So it's like a metal. We have plenty of materials which are crystals on Earth, but this of course is under much higher pressures. In fact, the pressures become so strong that eventually the neutrons start leaking out of the nuclei. They just sort of fall out of the nuclei and start moving around in the space between the nuclei themselves, along with the electrons. And this material is extraordinarily strong. It is maybe a quadrillion times as strong as steel if you try to pull on this material, because it's under such high pressures and it's so dense. When you go deeper, you start getting very exotic nuclei. So the nuclei at the surface are iron, essentially. But once you get deeper and deeper, what's happening is that the nuclear force is converting, well, not just the nuclear force, or the nuclear force is converting protons into neutrons, and you start getting very neutron-rich nuclei. So on Earth, the heaviest occurring nucleus is uranium-238, which has 92 protons and 146. So that is a neutron to proton ratio of maybe 1.5. In the inner crust of neutron stars, you can form much more exotic nuclei, such as zirconium-240 or maybe zirconium-540. So that is 40 protons with 200 neutrons or 40 protons with 500 neutrons. So this is a ratio of, what is that? Like 10 to 1, essentially, neutrons to protons. This nucleus, if it existed on Earth, would decay immediately. It would immediately undergo fission, but under the high pressures inside a neutron star, something like this could exist. What happens when you transition from the crust of the star, which is a solid, to the core, which is a fluid, can be very interesting. And in fact, the competition between the surface tension of the nuclei, which tend to hold them in spheres, and the electrostatic forces, which tend to repel positive charges from each other, means that non-spherical nuclei are possible. And physicists, being funny sometimes, decided, hey, what if we have these rod-like nuclei and sheet-like nuclei? What if we call this spaghetti and this lasagna? And these bubbles, these are gnocchi, and we have nuclear pasta. So this is very, very interesting. A bit speculative. We're not sure this exists, but if it does, it'd be very cool. I hope it exists. And this could also itself have interesting material properties because, for instance, it would be much easier to break these sheets in this direction than along this direction. So it could have important properties that affect sort of like the structural stability of these stars. In the core, all of the nuclei dissolve, and what you have left is a fluid, which is just a mix of protons, neutrons, and electrons. And so the composition of the core of the star is mostly neutrons, which outnumber protons by a factor of 10 to 1. And so that is why neutron stars get their name, because they're mostly neutrons. They're not entirely neutrons, but just mostly. So this reaction whereby the proton captures the electron, forms a neutron, and emits this neutrino is very important. So neutrinos are very light elements that don't like to interact with things. And because they don't like to interact, they like to fly out of the star very quickly. And this is actually how these stars cool. So there's no more heat being produced in these stars to lowest approximation. And so they just cool for the rest of time by emitting neutrinos from anywhere in the interior. The neutrinos can fly out from the core right out immediately, or light from the surface. And the cooling is dominated by neutrinos at early times and by light at late. But this cooling depends on the size of the star, the composition, what the layers are, how big the layers are, things like this. And so we can compare our modeling of what's inside the star to observations of the light coming from their surface to understand interior structure. And so that's actually part of the work I did. the inner core, the part which has the highest density, things get a bit less certain because our nuclear physics experiments cannot reach those densities. Essentially, this is matter which only exists in neutron stars. And so there are different possibilities of what we could find there. I think we will probably find what are called hyperons. And this is, you can find quark matter. Type of quark. So just a reminder that neutrons and protons themselves are not fundamental particles. They contain smaller particles called quarks, which come in different flavors. Not sure what they taste like, probably all the same. So up and down in neutrons and protons, and up, down, and basically strange in hyperons. And so it's the presence of these strange quarks that make hyperons unique. And so these are essentially heavier neutrons and protons. What happens if you combine all of these neutrons, protons close enough together is potentially the bounds between them dissolve and they essentially become a sea of these quarks. So, I hope this exists in the core of a neutron star. There is different properties, but we're not sure yet, and it's hard to determine for different. The fluid in a neutron star turns out to be actually superconducting and superfluid. So inside the cores, the neutrons and protons form pairs via the strong nuclear force, sort of demonstrated schematically here. So this is like what's called an electronic superconductor, which we find in metals on Earth, but it can occur at much higher temperatures because this strong nuclear force is attractive, and so they want to pair up, whereas on Earth, you essentially can't form the pairs between the electrons unless you get to cryogenic temperatures. You need liquid nitrogen at least, and more likely liquid helium to actually see superconductivity in metal. And superconductivity's main observational feature is that it leads to what are called pulsar glitches. And so the idea here is that the rotation of the solid crust of the star and the superfluid core of the star are different. And the transfer of rotation between one component to the other can lead to these sort of rapid spin-up events where the star is its period is slowly changing, and then it suddenly jumps up. It starts rotating much faster over a very short period of time. So the details of this are still highly debated, but it likely involves what are called vortex lines, which occur inside the superfluid. And these vortex lines can be thought of as mini tornadoes which thread the star and can get stuck to the neutrons, or the nuclei rather, the crust. And it is this ability of these little tornadoes to get stuck to the nuclei and to get unstuck, which leads to the glitching behavior. I will like to point out that one of the originators of a lot of these ideas of superfluid and superconducting neutron stars was Columbia University's Mal Ruderman. I think he would like to be shown with his brilliant diagrams of these flux tubes and vortex lines threading the cores of the star. Really original thinker, contributed a lot to our understanding of what's happening inside neutron stars. So this is essentially our current picture. We don't really know what's going on in the inner core, but everywhere else we have a decent idea, pretty good idea, especially the crust. And we have different components. We have the solid crust, possibly the tastophase transitioning from the crust to the core. We are threaded by extremely strong magnetic fields, and we have a neutron superfluid and a proton superconductor in the core. But I haven't really talked much about the magnetic fields yet, so let's get to that. So the fact that neutron stars are spinning down allows us to understand that the magnetic fields are strong. And by spinning down, what I mean is that they're slowly, very, very slowly, spinning at a slower rate. And so what we can do is equate the amount of energy that is lost from the star due to the fact that it's not rotating as quickly to radiation that it gives off. And the radiation that it gives off is proportional to how strong its magnetic field is. And so this allows us, just with measuring the rotation period of the star and how quickly it spins down, to infer what the magnetic field strength is. And so we can make a nice plot like this. So most of the neutron stars we observe are these radio pulsars, and so these black dots on this plot. But we also get the much more strongly magnetized stars, these magnetars shown up over here, which have fields of 10 to the 15, 10 to the 14. But there's a way to directly infer the field of a neutron star, which is using quantum mechanics and an idea developed by Landau, we saw earlier, and Columbia's own I.I. Rabi, which is Rabi-Landau quantization. Essentially, what this tells us is that electrons in a strong magnetic electrons are in this field, they have to be, in these discrete, levels, kind of like steps. And the idea is that if light is the correct frequency is shone on these electrons, they can jump up to a higher step. And so that is what we, in fact, observe. So what we see is we look at certain neutron stars, which are emitting X-rays. So these are ones which are accreting. They'll have electrons, in the space around them, and these electrons will be in a strong magnetic field produced by the star. We can see that the X-rays of a particular frequency get absorbed because the electrons will absorb this X-ray light, jump up the next energy level, and that sort of magnetic field strength around the star is. And for this star, a absorption feature at this energy corresponds to a field strength of 4 trillion Gauss or so. Finally, the most strongly magnetized neutron stars emission of X-rays and gamma rays, but they seem to be rotating very slowly. And so the energy has to come from somewhere else. It has to come from a very strong magnetic field. And so these stars, they have distinct X-ray and gamma ray emission features, which are possibly launched by magnetic explosions. Essentially, the magnetic energy has to be transferred from the interior of the star to the exterior. You can maybe build up stresses in the crust and break the crust, eject matter out, and this matter can emit high energy radiation, which is what is distinctive of these sources. So we have a nice animation on this slide of such a flare from a magnetar. So the magnetic field causes this matter to be launched out of the star, and as it's launched out, it's traveling very quickly, and it starts emitting high energy radiation. And so we've observed a few of these flares, but these are, there are more common types of high energy emission from magnetars, but these are sort of the signature feature of these stars. They have strong magnetic fields powering high energy electromagnetic radiation. So what does the future hold for instruments online? So this slide is showing essentially the newest instruments in the past 10 or so years, and for SKAO is not online yet. So CHIME, SKAO, and FOSS are radio, magnetic spectrum, primarily in radio and X-rays, but also we can use infrared to do things like find the neutron star in supernova 1987A. But more instruments looking, better instruments, find more sources, can tell us more about the masses in radii, particularly the mass out there. We also, of course, in the past 10 years or so, have gravitational wave observations. So from binary neutron star mergers. So we only have 2 confirmed binary neutron star mergers so far in gravitational waves. So this is an illustration of 2 neutron stars spiraling together, emitting gravitational radiation ripples in space-time before they finally finally merge and form maybe a heavier neutron star, maybe the heavy neutron star that immediately decays to a black hole, maybe a black hole immediately. It all depends on how massive the stars are and other properties. Finally, something which I find very interesting is asteroseismology applied to neutron stars. So star seismology is the study of the oscillations of stars. And so this is very interesting because it really tells you something directly about the interior of the star. It can tell you not just the mass and radius, but also the composition. It tells you what the layers are, again how big the layers are. What is actually in the cores of these objects potentially. And unfortunately, it's very hard to excite oscillations of neutron stars. Unlike the sun, there's no fusion going on, which is leading to the excitation of these modes. For the sun, we know hundreds of thousands of oscillations. For neutron stars, we don't know a single confirmed oscillation. But hopefully, they'll leave an imprint on gravitational waves. And if we combine that with the next generation of gravitational wave sources, hopefully we'll see some of these oscillations. Because the idea is that they can be excited by the stars when they spiral in on each other. The gravitational potential of one star excites the oscillation of it, excites the oscillation in the other star. So these next generation sources, or gravitational wave detectors rather, Cosmic Explorer, which will be in the United States, and the Einstein Telescope in Europe, will hopefully, tell us about, more neutron star mergers. Will tell us, more detail. The measurements will be more accurate, and also hopefully about something about the post-merger signal. What's happening once the stars actually merge? Because so far we haven't actually seen this yet. Anyway, that is all I have. So just to wrap things up, understanding neutron star interiors involves, the interplay of observations, theory, and computational modeling. Helps us answer some of the most intriguing, outstanding questions in fundamental physics and in astronomy. We've made a lot of progress considering, it's not really that many sources compared to other areas of astronomy, but there's still a lot of work to be done. And so I'll leave you with this brilliant composite photo of the Crab Nebula with the neutron star around there. Thank you very much.
All right, Peter, if you'll advance one slide. Okay. All right, if you have questions, you can raise your hand or you can type them online. If you scan this QR code, they'll go to my laptop and I will read them off. Let's see, I saw a question in the front. I will repeat every question. Go ahead. Yeah, so if there's so much pressure and so much gravity in a neutron star, how can there be this layer of plasma?
So you mean the layer of plasma on the surface, or? So the core, so the core is in fact a plasma, but the electrons and the electrons and the protons, they don't really move that far away from each other necessarily. They move very close to each other, but they're still far enough away that you can have electric currents or something in the core. So because the gravity doesn't really bind the electrons and protons together. That's a different force.
Yes, please. Yeah, if it's neutral with all those neutrons, how does a neutron star have such a strong magnetic field?
That's a good question. So essentially, there are electric positive and negative charges, the protons and the neutrons, and those are what are supporting these currents. That's what's supporting the magnetic field, rather. So the fact that these protons and protons and electrons don't really interact very much with the magnetic field. So it's if it was just neutrons, then yes, you wouldn't have any. But the fact that there is some means that you have the magnetic fields.
Right in the back. Yeah, so the question is, how do they detect gravitational waves from two combining neutron stars? And I will just take a moment to brag by proxy. Where I went to get my PhD, UC Santa Cruz, The team there was the first to look at the post-merger of two neutron stars in 2017, so it's very recent.
Yes, so gravitational waves from neutron stars are detected the same way that you detect gravitational waves from binary black holes, any other source, which is we have a few of these gravitational wave laser interferometers, two in the United States, one in Italy, and one in Japan. And what the setup there is that you have these long arms, which you're shining a laser beam down the arm, and you shine it in two different directions. And when the gravitational wave passes through the space that the light is traveling, it will produce this distortion, a very, very small distortion in space-time, and that will lead to a lag compared to the light traveling down the other arm. And we use that to infer that the gravitational wave has passed through the detector. So that is essentially how we do it. It's extraordinarily complex, sort of a marvel of engineering, really. And I remember being in grad school and they announced this, and I'm just like, I never thought they'd ever do this because this is so crazy. But they have. So.
Yeah, can you feel the gravitational waves when they pass through you? I don't think so for me either, but they do pass through us. LIGO is one of them. All right, I'm going to take some questions from online. What is the surface temperature of a neutron star, and does this vary?
That's a good question. The surface temperature of a neutron star does vary. Typical temperatures are maybe sort of less than 10 million Kelvin, but hotter than 100,000 Kelvin from sort of most of their observable life is the surface temperature. They're a bit hotter in the interior, mostly maybe like 10 to the 8 Kelvin in the interior for most of their life, maybe a bit hotter. They're born at above 10 to the 10 Kelvin, but they cool off very, very quickly.
Okay, I'll do another. What happens when a neutron star completely cools? Does it become something different?
Ooh, one thing is it's very hard to tell. I don't think it would become something different because the temperature really isn't supporting the structure of the star at all. It really is this, degeneracy pressure and this the strong force, and those really don't vary much with temperature. So, well, okay, degeneracy pressure does, but not really not at the temperatures we're talking about. So, basically, the neutron star just cools off and then just sits out in space, kind of living its lonely, cold existence for eternity.
All right, is there a question from the audience? Go ahead. So you asked about FRBs. We like to call them Furbies in astronomy, or maybe I just like to call them Furbies. These are fast radio bursts. So are they from neutron stars or other sources?
Well, so this is a very active field. We know one is definitely from a neutron star. It's from a magnetar. So this was detected in 2020 because we observed radio waves and X-rays from the same source around the same time. So we know, again, some FRBs are definitely from neutron stars, but we don't know if all of them are because FRBs can have a range of different properties. Some of them are repeating, some of them aren't. And so this is still an open question. But neutron stars being so compact, having such strong gravitational fields, they're certainly the leading candidate to be the progenitors of most FRBs.
Okay, I'm going to end with 2 questions online, but Peter will stick around. So if you have more questions, you're welcome to come down after we wrap up to answer them. There are so many good ones online, but I don't want to keep us here too much longer. But I'll ask, what is one thing that you most want to learn about neutron stars?
I think the one thing I'd most want to learn is whether there's deconfined quark matter in the cores, because deconfined quark matter can have very interesting properties in different phases. And one I'm very interested in because of how crazy it is called a color superconductor. And this is a stage of matter where essentially it's like a electronic superconductor, but the charge which is carried is the color charge of the strong force. And we know no other place in the universe where this could exist. And hopefully it has some observable features that we could tell spot on that this is a color superconductor in its interior. But again, it's very hard to determine these things. But I hope that there's deconfined quark matter in neutron stars and that it is a color superconductor.
If my last name were Quark, I would have been forced to be a physicist instead of an astronomer. All right, I'll end with one question, kind of going back to a 1,000 kilograms on average. Our sun weighs about 2 times 10 to the 30 kilograms. So if you divide those two, it's about 3 times 10 to the 26 elephants for our sun. So I don't know what 10 to the 26 is as a word. It's certainly more than trillion. Maybe it's septillion. I don't know off the top of my head, but that is how we would do the math for that question. All right, let's thank Peter again. And before you all leave, we're going to do a raffle, so you definitely don't want to leave yet. How we do this is on your chair on the seat